Hello and welcome. This is Mr. Robinson's Chapter 5 video review for homework number 9, Chapter 5 closure. What I mean by that is I will use these problems and solve them for you. And these are the example problems we'll use. I'm not going to do any notes in between. And as you can see at this time right here, I have class in less than an hour. So I am going to go through this actually really quickly. I'm only going to do one type of thing per problem, if that's okay with you guys. All right, so let's get started here with number 90. We have two brothers, Martin and Morris. They are in their backyard. Morris is taking down a wall on one side of the yard while Martin is building a wall on the other side. Now, Martin, who is building the wall, starts from scratch. So starting from scratch means that he didn't have anything to start with. He had 0 bricks. And he lays 2 bricks every minute. Meanwhile, Morris takes down 3 bricks each minute from his wall, and it takes Morris 55 minutes to finish tearing down his wall. So we don't know how much Morris started with. In fact, that's what part A asks you to figure out. How many bricks were originally in the wall that Morris started tearing down? So he did 3 bricks per minute of tearing for 55 minutes. So if he tore down that many, you're going to do that multiplication, 3 bricks every minute for 55 minutes. So after 1 minute, he's done 3. After 2, he's done 6, etc., up to 55. So you can either add 3 55 times or do 3 times 55, which is 165 bricks. You're going to do this a lot in chemistry, this whole unit conversion and cancellation. Notice how minutes divide each other out. So that's kind of nice. Okay, represent this situation with 2 equations in a graph. So I'm going to use Martin as red. Let's go with him first. It seems like his is a little easier to use here. He does 2 bricks every minute, and X here represents number of minutes. And Y is number of bricks. Okay. So when we have that, let's go ahead and say every single time I go up 1 minute, how many bricks did I go up? And that's really the idea behind this problem. So you do minutes and bricks there. And so for Martin, he started from scratch. So if we have some Y equation for his number of bricks, it's 2 bricks every minute. Y equals 2x. And if you want the starting value, it really is plus 0, if that helps. Okay. Morris, on the other hand, he takes down 3 bricks every minute. So while this guy builds, he's going up in that positive direction. This guy's going down. He takes down 3 bricks every minute. Every time 1 minute goes by, he loses 3. That's what that means. But we also need a starting value for this guy, and his was 165. That's what we had to find. Looks weird. Okay. That's also your y-intercept, and this is a value that we need to be able to graph on here. And this only goes up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points here. So that means to fit 165, you need these to go up intervals of, well, more than 15. Because up to 15, that would give you 150 here. So I'm going to go up, well, you know what, if I went up every 15, this would be 165 right here. So I wouldn't be too disappointed in having that right there. So if I go up every 15, I need that scale. This is 15, this is 30, 45, etc. This here is 150. Now my x scale doesn't have to be the same. In fact, it shouldn't be the same. Well, you know what? Perhaps it should. We might need to do something to represent how many times we go over something. But I'll go ahead and go over 55 minutes here. I want to be able to get this 55 going on. So I'm going to go let's just go every 15. So we can talk about slope. This is 15, this is 30, etc. You keep going, this is 150. Okay, so let's go ahead and check this out. Now, slope is rise over run. As long as I can equate these things as the same amounts each time, every time I go up 1 here, or 15 here is going over 15 here, then I can use these slopes to graph these as well. I don't have to do tables. So for instance, for my red guy right here, I'll go and do him first. I start at 0 right here, and every single time he goes, I'm going to go up 2 and over 1, up to and over 1, like so, up to over 1, etc. And let's go ahead and look at what those actual numbers are, because this isn't really going up 2 over 1, but that is the rate. Every time I go up 30, every time he builds 30 bricks, it takes him 15 minutes. That's what that means. And does that make sense with this problem? Yeah, absolutely. If he does 2 bricks every minute, he would do 30 bricks every 15 minutes. So notice that that slope is the same, and that's exactly why I agreed upon myself to keep with that interval there. And normally your graph would probably go in the negative direction as well, but for the sake of this word problem, I'm just going to make the graph look like that. In fact, I'll make it a little skinnier, because I want to find the point of intersection. It looks like that's what part C is going to be about. Let's go ahead and do the green guy now. Martin, I do believe. Okay, so he's going to go down 3 and over 1, it looks like, negative 3 over 1. So every time he lays 45 bricks, it takes him 15 minutes to lay 45 bricks. That's what that means. Just as it takes him 3 minutes. Did I say that right? It takes him 15 minutes to lay 45 bricks, just like it takes him 1 minute to lay 3 bricks. So I'm going to go and draw it this way. All right, it's going to go down. And actually, I'm just going to go and stop it right there. Really, once he gets to 0 bricks, he's not going to start laying negative bricks, so that kind of becomes an obsolete and moot point. The final question they ask here is, when did the 2 walls have the same number of bricks? So we're going to solve for x. That's the thing that we don't know. But the more important thing is we need to find this point on the graph. Now, it's right there, and that is not a distinct point which you can discover just by looking at it and say, you know what, I think I know what it's about. No, you have to solve for it. And to solve for it, you have to use what's called the equal values method. That is what will allow you to say when your 2 y values are equal and when your 2 x values are equal. So if we have a system of equations here, we want to set if y equal to y, right? We want the same height, which means we want this to equal this. So we're going to say 2x plus 0, which is just 2x, equals negative 3x plus 165. Okay? So when I add 3x to both sides, I'll get 5x equals 165. And when I divide both sides by 5, you can use your calculator. I think this is, let's see, that's 150. So that's divided by 5 is 30. So there's another 3, so that's 33. So x is 33, and that's not enough to just say what 33. We need units. This is 33 what? When did the 2 walls? That's your x value. When, and this is all in minutes. Took 33 minutes for them to have the same amount of bricks while Martin was tearing, Morris was building, or the other way around. Morris was tearing. Okay, so that 33, you can see there's 30, here's 45. This is in between. Not exactly a decimal, but it's in between your increments of 15. So you do need to be able to find it that way. Okay, rewrite each of these products as a sum. Make sure to use a generic rectangle to multiply. Okay, so this isn't forcing me to do that. I will with the last problem. I'll do the first and last problem. I will also use arrows, if you don't mind. I'm just going to start just by building just a really generic rectangle. In other words, I'm going to use the same rectangle for every problem. Okay. In this first problem here, first of all, you have to recognize where your products are lying. So my product is 6x, I can represent, say, as my height. And 2x plus y minus 5 I can represent as my base. So this is my product. This times this. Height and base. So if 6x is my height, maybe it's right there. And 2x plus y minus 5 is my base, then they'll be right here. I have 2x plus y minus 5. Okay, so now use the generic rectangle, multiply individual base times height. 6 times 2 is 12, x times x is x squared. 6 x times y is 6xy. 6 times negative 5 is negative 30. And there's an x at the end there. You can't combine any like terms, and that will be your final result. You'll get 12x squared plus 6xy minus 30x. The order doesn't necessarily matter. You have to make sure that you combine like terms, though. Now we have that, and I also want to show you through means of arrows as well. Generic rectangles are great, and never stop using them. In fact, I teach Algebra 3-4 over at Burlingame. Some people still use that. They call it the box method, but it's the same exact thing. There's no idea that you have to draw rectangles in any sort of form. Just make sure you have every term divided. The next way is called the arrow method. Well, I'm not sure what it's called. It's called distribution. And what you do is you take this 6x and you multiply it by every term that you have. You basically do the same thing as you did before. Only when you practice this more, people use this as a mental math approach. So they kind of do this in their head. They say, what's 6x times 2x? That's 12x squared. What's 6x times y? 6xy. And what's 6x times negative 5? Negative 30x. And you get the same solution here as you did here. And that's it, and that's all. Let's go ahead and do B now. I'll just use generic rectangles for this. 2x minus 11. And see, this is why this rectangle. It's going to be a larger rectangle. 2x minus 11 and x plus 4. So we're going to multiply each guy. Now the idea of rectangles is when we divide this, we're saying that if this is x, so is this over here. And if this is 4, so is this over here. Likewise, this is 2x, this is negative 11. That way, if you can't find, oh, what do I multiply this with over here? Oh, with that 4, because this is 2x and this is 4. So 2x times 4 is 8x. 4 times negative 11 is negative 44. Negative 11 times x is negative 11x. And x times 2x is 2x squared. So I need some room to write my result. I'll go and do it right up top here. This gives me 2x squared. And check this out. I'm going to do this right here. This is plus 8x minus 11x. So we got to combine like terms there. That gives you negative 3x minus 44. And I'm just going to stop right there. You know, once again, this is going to be a time presser for me. I'm definitely going to have to speed up as I go. So anything that sounds the same through this, like I said, I got to stop doing. 7x times 2xy. Really, I would say do not do a generic rectangle for this. You already see what you have to multiply. There is no separation of terms. We just have to do 7x times 2xy. So 7 times 2 is 14. X times x is x squared. And y is left there. One thing that might help when you do multiplication here is if you rewrite these terms. Multiplication is commutative. And what that means is I can reorder how I multiply these guys and I won't change the result, the product. So I can write 7 times 2 if I want, then x times x, and then y right there. So that might help you be able to write 14x squared y without leaving out possibly one of your answers. Okay, let's go and do the final one here. X minus 2, generic rectangle first. 3 plus y. Whoa. Okay, x times y is xy. Negative 2 times y is negative 2y. Negative 2 times 3 is negative 6. X times 3 is 3x. So we're going to end up with 4 different terms here. They do not combine. xy plus 3x minus 2y minus 6. Looks a lot like that group test problem, only it had x plus 2, I do believe. So there's your final result. Let's do the arrow method one more time. Now, the whole idea of arrow method, as you saw, was I multiplied this outside guy by every term. I have to do the same thing, only you have to realize that this guy, if you want to call it the outside guy, it has 2 different terms. So I'm going to have to take one term at a time. I'll do x with these 2 guys. And I'll do, be careful, negative 2 with these 2 guys. So that's a negative 2. So I'm going to rewrite this whole thing. I have x times 3 plus x times y. Here we go. Plus negative 2 times 3 plus negative 2 times y. And like I said, people will do this mentally sometimes. So you can check this out. We're going to do x times 3 gives you 3x. X times y gives you xy. Negative 2 times 3 gives you negative 6. Negative 2 times y gives you negative 2y. So that's where you get all your results, just like we did before. Okay, find the missing areas and dimensions for each generic rectangle below, then write each area as a sum and as a product. Oh, by the way, these top ones up here, these were our sums. Here's a sum, here's a sum, not there, sum and sum. So we have our 4 sums written out, and that is basic. It's the area of the inside guy. Generic rectangles are nothing more than inside areas of inside guys. Okay, figure out the missing information. This ends up working kind of like I won't say a puzzle, but you got to use one clue at a time and build up from that. Like, I don't know what this is without knowing other information. Same with this. What I do know is this area is 16x squared. Means I did 8x times something to get 16x squared. Well, 8 times 2 is 16, and x times x is x squared, so that gives me that. What this allows me now to do is find out other information here. For instance, I know this is 2x. I know this is 8x right here. So I need to figure out what to multiply this by and this by even to get 1 here. Whatever's going to be here, this will be 1 times 1. So if this is 1, so is that. If this is 1, so is that. So now I've kind of written out all my stuff that I need. Let's go and fill out the rest. 8x times 1 is 8x. 2x times 1 is 2x. And I have to write this now as a product and sum. So I have base and height as 2x plus 1 times 8x plus 1. That's my product. My sum is 16x squared. Then I have 8x and 2x added together. That's 10x. And then 1. And that's your final result. Okay, let's keep going. Part B. Negative 3, negative 12x. So it looks like this guy will have an x in here. Negative 12 divided by negative 3 is positive 4. So this number is a positive 4. If that's a positive 4x, so is this over here. 4x times 2y. We get 8xy. All right, this is 2y, then this is up here. 10 divided by 2 is 5. And it looks like the y's are taken care of over here. So if this is 5, then so is that. And this must be a negative 3 up here. 5 times negative 3 is negative 15. So here we go. Base times height. 2y minus 3 times 4x plus 5. There's base times height equals my sum, excuse me, 8xy minus 12x plus 10y minus 15. There's your final solution. And again, order does not matter. Just make sure that you have the negatives where they're supposed to be, as long as you combine like terms. Number 93, for each equation below, solve for x. So you can do this using generic rectangles or arrows. I'll go and do generic rectangles for this one and arrows for this one. So you don't need generic rectangles to rewrite the equation. I'm just going to go ahead and draw these boxes to say I need to figure out what these sums are. And then after that, I'll just rewrite my equation using my sums. Because your first step in solving these equations is simplifying your equations. We need to expand these, combine like terms, all that good jazz. So I have x negative 1, and sorry for the sloppy boxes, x and 7. X times x is x squared. X times negative 1 is negative 1x. X times 7 is 7x. 7 times negative 1 is negative 7. So this final result right here is x squared plus 6x, that's 7x minus x, minus 7. Okay. I need something else on this side now. I have x plus 1 times x minus 3. So we'll have x times x, which is x squared. X times 1, which is x. X times negative 3 is negative 3x, and negative 3 times 1 is negative 3. Okay. So now we have x squared. Negative 3x plus 1x is negative 2x, and then minus 3. So we've accomplished step 1. We've simplified this equation. Now let's go on to step 2. We have to isolate x. And we haven't really dealt with quadratics too much yet, especially not in ways where you have to solve for some big guy. I'm going to subtract x squared from both sides, and it looks like they cancel out just fine. So this is taken care of. If that doesn't get taken care of, you might have been doing the problem wrong, because we're not setting it up for you to solve for quadratics yet. Linear equations, the single x values, of course. So let's isolate these guys. Let's add 2 x's over here. So I have, boom, cancels out there. 6x plus 2x now becomes 8x. So I have 8x on this side. Now I also have to take care of my negative 7 over here. Add 7, and this goes away. And then I get, on this side, negative 3 plus 7, which is 7 minus 3, which is 4. So 8x equals 4. Divide by 8 on both sides. You'll get x equals 4 over 8. Now 4 over 8 reduces to 1/2. Or if you wrote 0.5, that's good as well. And you can double check that. Speeding up here, let's go ahead and use arrows for this one. Main reason why I want to do arrows is to say if you decide to use arrows, make sure you know what you're distributing. I have a 2x to start off with, but this guy needs to distribute. and this is a negative 5. It's not a positive 5. So negative 5 is going to multiply with x and with 4. And I'm also going to take this negative 2, and I'm going to multiply it with x and 3. Okay, so my next line will say 2x, this guy right here, and then I'm going to have negative 5 times x is negative 5x. Negative 5 times 4 is negative 20. So notice how this became a negative 20. A lot of people are going to put positive 20. I'm forewarning you to make sure you don't make that mistake. Negative 2 times x is negative 2x, and negative 2 times 3 is negative 6. Okay, so I'm going to simplify just a little bit more. Combine like terms here. I get negative 3x minus 20 equals negative 2x minus 6. A lot of negatives here. What you actually can do in this case is you can multiply both sides by negative 1. Like boom, boom. You can switch. As long as you switch every sign in an equation, everything can literally be switched. So basically everything can become positive. 3x plus 20 equals 2x plus 6. Same exact equation. Not that you have to do that, but if you want to follow my steps, go ahead. Simplify now. Subtract 2x. And we're also going to subtract 20 to isolate. All right? And we will get over here x, just 1x is exactly what we want, equals 6 minus 20 is negative 14. You can double check that as well. So two different methods there. Going to move on down. For each equation below, solve for y. All it means to solve for y is get y by itself, just like we get x by itself over here. So we have to simplify, isolate, divide. Everything's simplified as much as we can. Now we have to isolate. So by isolate means get rid of this 6x. Let's get it over on this side. Subtract 6x, subtract 6x. You get 0 over here. We bring down the negative 2y, not a positive 2y, right? So we get negative 2y equals. Now I've seen this a lot before. They'll 4 minus 6x. They'll put negative 2x. And it's not going to be negative 2x. You can't combine like terms there. This is literally, these are two different terms. You can't do 4 minus 6x, so write that out as 4 minus 6x, or negative 6x plus 4. If you're used to this form, this y equals mx plus b, when we've been doing rules, we normally write our x value first. No particular reason other than keeping with the form, but that acts as your slope. Let's go and finish this off. Divide by negative 2 on both sides. Now in order to do this, you have to divide by negative 2 with every term here. Some people will write it all over 2. That's fine, as long as you divide every term by negative 2. So this becomes y equals negative 6 divided by negative 2 is positive 3. 4 divided by negative 2 is negative 2. So y equals 3x minus 2. Okay, next one right here. Same thing, solve for y. So let's get all of our y's on one side of the equation and everything else on the other side. I'm going to go ahead and move my y's over here. So I'm going to add 2y to start. Add 2y, add 2y. And notice how I'm going to write it right underneath something here. In fact, what I should have done, this minus 6x, I really should have just written it over here. Because that'll allow you to say, okay, I can't combine these like terms. I'm only going to put things underneath what I can combine. Maybe that'll help you out in the long run. What I'm also going to do is subtract 6x, because like I said, I wanted to move anything else over here. Subtract 6x, and notice I'm writing it right under the x value there. The 8 stays where it does because it's on the correct side. And out here I'll get 3y plus 2y, which is 5y, equals negative 2x plus 8. Now I have to divide everything by 5, both sides. And I'm going to write it the different way. I'm going to say divided by 5 and all divided by 5, just to show I'm going to get the same answer. 5 over 5 is 1, so we'll get y equals negative 2 over 5x plus 8 over 5. I want to leave that as a fraction. There are decimal equivalents. That would be negative 0.4x plus 1.6. You can use that, but I'm not too concerned one way or the other. Now these are written as rules. Notice how there's a number in front of x. That's your slope, and this is your growth, your y-intercept, your starting value. Now they do say find the growth factors and y-intercepts for the equations in parts A and B. Now they are located here. For part A, my growth factor is 3, or 3 over 1 if you want to write it as a slope. And my y-intercept is, it's -2, but it's at the point 0, -2. Maybe that's a little more beneficial to write. For part B, your growth factor is -2/5, and your y-intercept is 0, 8/5. Perfect. For every 42 berries Samantha picks, her dog Klepto, nice name, eats 7 berries. Samantha picked 462 berries last Saturday. How many berries did Klepto eat last Saturday? Answer this question by writing and solving a proportion. So you see this as a proportion, and you know it's a proportion because proportions are all about something directly affecting something else. Meaning, let's say Samantha didn't pick any berries. Let's say she picked 0 berries. Klepto will be eating 0 berries. How many she picks directly influences how many Klepto eats. And if she doesn't pick any, Klepto can't eat any. So that definitely is a proportion. So I'm just going to write this as a ratio here for 42 over 7. Every time Samantha picks 42 berries, Klepto eats 7 of them. Now I can reduce this fraction. This reduces to 6 over 1. That just helps me in the long run so I can use smaller numbers. So 6 over 1, so this is the ratio. It means every time Samantha picks 6 berries, Klepto eats 1. That's the rate we're going by. Samantha picked 462 berries last Saturday. So setting up a proportion, Samantha is there, and Klepto is your x. Right there, it's your unknown. How many did Klepto eat? So a lot of different ways you can do this. You can talk about cross multiplication, this and that. I'll do cross multiplication for this one, and I would like to offer a lot of different ways. I don't know if time is with me here, so I'll go ahead and avoid that for now. I'll give you one of them, cross multiplication. 6 times x equals 462 times 1. Now notice, you would have had to use a calculator for that part. Do 7 times 462 and all that. Divide both sides by 6. I don't have a calculator in front of me, actually. That's why this is a problem. So I know that 420 is 6 times 70, and there's 42 more after that, so this must be 77. That's one of those number talk things, right? So Klepto would have eaten 77 berries if Samantha picked 462. Klepto is eating a lot of berries. After Klepto is finished eating, how many berries did Samantha take home on Saturday? Oh, that's kind of a nice question. So it's saying that Klepto finished eating. Samantha picked 462 berries Saturday. Klepto ate 77 of them. And this is how much is left. What is that, 385? I like this question because, I mean, like the reason why I was like, oh, is because we don't really talk about this kind of problem. I mean, but the whole idea of Common Core standards and the CPM book that we use and such is that you're supposed to identify with the words, and this isn't about formulas, this and that. This isn't the difference formula, but you get an understanding if you can put it into words. Like I did. She started with 462, Klepto ate 77, Samantha has this many left. Right? There is still a difference there, so that is why I do like this problem. It's pretty nice. Okay, solve for each variable. So this is where I wanted to talk between cross multiplication, this and that. This is all cross multiplication is. First of all, I'll write this as cross multiplication, but then I want you to see how this becomes. So 10x equals 21. So how did we get to that? How did they say all you got to do is move these over and multiply? Well, the whole thing about it is cross multiplication it's great. It's a great method. It really is. It helps you clear fractions. You do it in one step. Technically, it's never wrong. The math behind cross multiplication is kind of iffy. You can't just say, I take this 10 and multiply it this, I take the 7 and multiply it this. You can use the method in the end, but what really happens is, I'll do this in 2 steps. I'll use a different color. If I want to eliminate this 10 on this side, I would multiply both sides by 10. Because what happens here is this is 3 times 10, all divided by 10. And 10 divided by 10 is 1. So all I have now is 10 times x over 7 equals 3. The next thing I want to do is say, well, I don't like the 7 either as the denominator. Okay, no problem. Multiply both sides by 7. Remember, whatever's affecting some value, you can reverse the operator, and that will be gone. That's all that will be left. So divide 7 over 7 there, and 3 times 7 here is 21. That's where we get 10x equals 21. I had to write more steps here. I had to do 2 more things. Well, I didn't have to, but if I have to write that out, it might take longer, but that still gets you to here. And then you divide both sides by 10, and you'll get x equals 21 over 10. That does not reduce, so I'm going to leave it like that. The other way to do this problem, really, if I rewrite this really quickly here, is this is all about isolating x. So if you do cross multiplication, you'll do one more step than you need to. And that's really the other thing about these problems. I'd really like you to see the problems as they are. Isolate x, get it by itself. It's dividing by 7. What do? Multiply both sides by 7. Now you get x equals 3 times 7 is 21 over 10. I didn't have to do 2 steps. That's it. I didn't have to bring 10 over here, but if you see it without fractions better and you appreciate that more, then that's good. All right, for part B, we have 8 over m, and that equals 3 over 22, and that's another proportion there. We have to solve for m. So m's in the denominator here, and one thing a student pointed out was they said, well, we want m in the numerator, and we know something about proportions. As long as we do one thing to one side, we can do something to the other side. If I want to flip this over as m over 8, I can, as long as I keep everything in proportion. This can be 22 over 3 instead of 3 over 22. Recall in the previous problem when we had Samantha and Klepto here, I didn't have to write this as 42 berries for Samantha and 7 for Klepto. I could have written as 7 for Klepto over 42 for Samantha. That doesn't matter as long as I keep the proportion the same. I would have had to equal x for Klepto and 462 for Samantha here. Still gives you the same result. So now I have this somewhat easier for me because I need to solve for m and I need m in the numerator. I'll do the same thing as I did last time. I need one step for this. M's being divided by 8. We can multiply both sides by 8 and it'll be taken care of. Take out your calculators. 22 times 8. I get, what is that, 176 divided by 3. Now, does that divide by 3? It does not. So that's it, and that's all. Please leave it as an improper fraction. Do not round the decimal. Mixed numbers are okay, but you don't want to be wrong with that either. Finally here, 11 over 5 equals 2p over 3. Okay, I'll do cross multiplication with you once. Take care of that. 3 times 11 over here. 5 times 2p over here. We still have to divide anyway. That's why I don't mind doing cross multiplication for one of them with you, but make sure you understand what's happening to it. We divide both sides by 10, and we get p equals 33 over 10. These problems really did not like you breaking down fractions or having clean numbers, so you have a final solution there. Okay, number 97. Kirsten enlarged her favorite picture below on her computer so that the enlarged figure was similar to her original drawing. The word similar means in proportion. It means proportional. It means the figure is the exact same, only a bigger version. Like if somebody makes a small replica of like a baseball stadium, everything is supposed to be drawn to size, but maybe a smaller version of it. So we have these proportions here. Let's say we call this the, it says if the measurements of the original and new figure are as shown in the diagram at right, find x. So pretend like this 3 here happens to be the width of this, I guess it's a turtle. The width of this turtle right here. So that's 3. Maybe call that the base. And maybe the turtle's 5 feet tall. And then she enlarged the picture so that the base now is 7 feet and the height is now x feet. We need to figure out what that height is. That's all we're trying to do. So now we have this proportion. And you can write this a lot of different ways. That's kind of the thing I was talking about before. I'm running out of time, but I think I'm near the end here. We'll say if we do basis to height as basis to height, we can say 3 over 5 is equivalent to 7 over x. 3 over 5 is equivalent to 7 over x, meaning this is base to base and height to height. So we can write it that way. You can also write 5 over 3 equals x over 7. For the same reason, we can flip then. What else you can do is you can talk about small to large. So I can say the base in the small grows to the base in the large, as the height in the small grows to the height in the large. And you can flip those as well. So all proportions can be rearranged 4 different ways exactly. No more, no less. There can be 4 different ways you can rearrange these proportions. And notice they all look different, but they all have the same correspondence with one another. And it doesn't matter which one you use. But I'm going to go ahead and decide to choose one of these two, because if I want to solve for x, I want it in the numerator to start with. Otherwise, you'd have to flip it anyway, and you'd be right back to where you were. Let's go and solve for both to show you that it's the same thing. If I multiply by 7 on both sides here, I'll get 7 times 5 over 3, which is 35 over 3. That is 35 over 3. Over here, if I multiply both sides by 5, I'll get 5 times 7, which is, again, 35 over 3. So I get the same answer, despite a different setup. What I can't do is do something like 7 is to x as 5 is to 3. What you always want to do is map your arrows so that they go the same way. So for instance, when I did this one right here, 5 over 3x over 7, I did arrow, boom, arrow, boom. It should draw the same way, in the same direction from the same place. 7 over 3 and x over 5 was boom, 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 boom. Notice how the arrows do the same correspondence. That might be a good thing to practice. I think this is the last problem, which would be really nice. I'll finish on time. Find x and y for the system of equations below. Equal values method. Once again, the whole idea about equal values method, solving the system, means finding the x, y value for when these guys intersect on a graph. If you drew them, what x value, what y value do you have? And the idea is you have the same x and y value, meaning this y equals this y, meaning this equation equals this equation, which means this guy equals this guy. So for that to be true, let's set those two equal to each other. 3x minus 5 equals negative x plus 23. And you solve the rest of the way. The thing is, though, we're not done once we solve for x. We also have to solve for y. So I'm going to add x to both sides. I'm going to add 5 to both sides to isolate. And I now have 4x equals 28. Divide both sides by 4. You get x equals 7. So we solve for x, but you have to solve for the system. Like, you need to write this in the end as 7 comma something. So I still need a y value. In order to find that y value, I have to insert the 7 back into either equation. It doesn't matter which one. I'm going to go and use the top one because I think dealing with this negative here would be more of an issue. So I'm going to do 3 times 7. Y equals 3 times 7 minus 5. So y equals 21 minus 5. Y equals 16. So you get 16 here. And if I plugged 7 into this one, I'd get the same thing. Negative 7 plus 23. That's your final solution, and that's it. I'm going to quickly go back to that one problem, the graphing one. I think it was the first problem, actually. This guy right here, they only asked us how long it would take for them to be at the same number of bricks. If you wanted to find out how many bricks that was, you'd have to plug in 33 into either of these equations. Let's say I went for Martin building his bricks up. He does 2 bricks per minute. So if Martin does 2 bricks per minute, you do 2 times 33, and you'll get 66 bricks. That means that both Martin and Morris were at 66 bricks after 33 minutes. That's what you were trying to find out. Not that they asked you how many. But make sure you answer the questions. Anyway, it's 7:50. I fear I've run out of time, but I think I did pass. Let me make sure I've done all the problems. Please rewind anything that you need, and perfect. Awesome, I got through it. So any other questions you have, go and ask away.